Dear students, I am M. Nazreen Banu, Associate Professor, Department of Mathematics, Muthaimal Engineering College, Rasibram. Welcome to this lecture. In lecture 1, we have seen MM1 Infinity FCFS queuing model, that is single service queuing model with infinite capacity. In lecture 2, we have seen MM1 NFCFS model, that is single service model with finite capacity. That is in model 2, the capacity of the system is limited to n. Now we will see model 3. Model 3 is MMC Infinity FCFS model, that is multiple service model with infinite capacity. In this model, capacity of the system is infinite and number of counters are greater than or equal to 2. Next, measures of model 3. In this model, lambda n equal to lambda for all n. Here lambda by C mu, that is rho is called lambda by C mu, which is less than 1. So rho is less than 1 means lambda by C mu less than 1 implies lambda less than C mu, and mu n equal to n mu if 0 less than or equal to n less than C. That is the number of customers less than number of channels means we have to use n mu, and number of customers greater than number of channels means C mu. Here C is called number of servers, that is channels. Next, formulae. Probability of no customers in the system, that is P naught, which is equal to summation n equal to 0 to C minus 1 lambda by mu whole power n by n factorial plus lambda by mu whole power C by C factorial into C mu by C mu minus lambda to the whole inverse. We can write like that also, P naught equal to 1 by 1 whole divided by summation n equal to 0 to C minus 1 lambda by mu whole power n by n factorial plus lambda by mu whole power C by C factorial into C mu by C mu minus lambda. That is formula 1. Next, second formula we will see probability of n customers in the system is, that is Pn equal to 1 by n factorial into lambda by mu whole power n into P naught if 0 less than or equal to n less than C. It means number of customers less than number of channels means we have to use the first formula, and number of customers greater than or equal to C means we have to use the second formula, which is 1 by C factorial into C power n minus C into lambda by mu whole power n into P naught if n greater than or equal to C. Derivation also here it is available, but no need derivation and all, no need, directly you can take the formula and proceed. Next, formula 3, average number of customers in the queue or average queue length, that is LQ equal to 1 by C into C factorial into lambda by mu whole power C plus 1 whole divided by 1 minus lambda by C mu to the whole squared into P naught. Next formula, average or expected number of customers in the system. We can use the remaining formula. Using Little's formula we can find LS is nothing but average number of customers in the system, which is LQ plus lambda by mu, and the fifth formula is average or expected waiting time of a customer in the system, which is WS equal to LS by lambda, and expected number of customers in the queue is WQ equal to LQ by lambda. That one is sixth formula. Next we will see seventh one, probability that an arrival has to wait. Okay, that arriving customer has to wait means we have to use this formula, probability of WS greater than 0. It means number of customers more than 0. 1 minimum 1, it means lambda by mu whole power C into P naught by C factorial into 1 minus lambda by C mu. P naught already I have given the formula, that formula should be applied here. Next formula, probability that an arrival enters the service without waiting. It means we have to use the formula 1 minus probability of an arrival has to wait. Okay, without waiting is nothing but 1 minus of probability of an arrival has to wait. We have to use this formula, that is 1 minus lambda by mu whole power C into P naught divided by C factorial into 1 minus lambda by C mu. Next formula, mean waiting time of a queue for those who actually wait is given by W such that W greater than 0, which is equal to 1 by C mu minus lambda. This formula we have to use mean waiting time of a queue. Next formula, probability that there will be someone waiting, that is probability of n greater than or equal to C plus 1, that is number of customers greater than or equal to C plus 1 equal to lambda by mu whole power C into P naught by C factorial into 1 minus lambda by C mu into lambda by C mu. This formula we should use. Compare the model 1 and model 2. Model 3 have little bit difficult formulas are there. Okay, so we have to memorize this formula, probability that there will be someone waiting. Particularly we have to find we have to memorize the formula like P naught Pn and Ls. The remaining formulas can be, we can use Little's formula to find the formula for LQ, WS, WQ, etc. Next, average number of customers in non-empty queues, that is who have to actually wait, is given by LW equal to lambda by C mu divided by 1 minus lambda by C mu. This formula we have to use. After that, average number of ideal servers, which is equal to C. C means channel. C minus average number of customers served. Next formula, efficiency of MMC model, which is equal to average number of customers served by total number of customers served. These are all the important formulas. We will see the problem now. Problem 1. A supermarket has 2 servers servicing at counters. Okay, see here the first line, 2 servers. Okay, so C equal to 2. Channels, number of channel equal to 2. The customers arrives in a Poisson fashion at the rate of 10 per hour. The service time for each customer is exponential with mean 4 minutes. Find first subdivision, the probability that a customer has to wait for service. Okay, it means that particular customer has to wait for getting service. It means the customer should be in queue. Okay, so you have to find the waiting time of a customer in the queue. You have to find, that is WQ. You have to find. Second one, average queue length. Okay, and third formula, the average time a customer spends in the queue. It means average time, the amount of time a customer spends in the queue. Third subdivision, we have to find out WQ. For first subdivision, you see the probability that the customer has to wait for service. Okay, for getting service, okay, that one is waiting time of a customer in the service. So WS, first formula WS, okay, second formula LQ, and third formula WQ. So this is of model 3. You see solution, MMC infinity FCFS, n is not given, so we have to take it as infinity. MMC infinity FCFS model, mean arrival rate equal to lambda equal to 10 per hour, mean service rate equal to 4 per minute, which is equal to 4 by 60 per hour. Okay, that is 4 per minute. Okay, so you have to convert into hour. So 1 minute equal to 1 hour equal to 60 minutes. Sorry, mu equal to, you see, 1 by 4 per minute. Mu equal to 1 by 4 per minute. So 1 by 4 into 60, so that it will be 15 per hour. Next, P naught equal to summation n equal to 0 to C minus 1 lambda by mu whole power n by n factorial plus lambda by mu whole power C by C factorial into C mu by C mu minus lambda to the whole inverse. With substituting the values of lambda, mu and C. Here C equal to 2 channels. So summation n equal to 0 to 2 minus 1, 10 by 15 whole power n by n factorial plus 10 by 15 whole square by 2 factorial into 2 into 15 by 2 into 15 minus 10 to the whole inverse. Using calculator, you can find the value of this. So see sigma n equal to 0 to 2 minus 1 is 1. 2 by 3 whole power n by n factorial plus 2 by 3 whole square by 2 factorial into 30 by 30 minus 10 whole inverse. You see n equal to 0 to 1. First you substitute the value of n, which is 0. So first term will be 2 by 3 whole power 0 by 0 factorial, and the second term will be 2 by 3 whole power 1 by n factorial. Okay, so using calculator simplify, you will get 0.5. So probability of no customer in the system is 0.5. Next, first subdivision, the probability that a customer has to wait for service. It means probability of W is greater than 0. That formula now we have to use lambda by mu whole power C by C factorial into 1 minus lambda by C mu into P naught. Substituting the value of lambda, mu and C, P naught, etc. Simplifying, you will get 0.167. Next, average queue length, which is LQ equal to what is LQ? Lambda by mu whole power C plus 1 by C factorial into C into 1 minus lambda by C mu whole square into P naught. Substituting the value of lambda, mu, C by mu. Okay, substituting the value of C, mu, lambda, etc. Simplifying, you will get 0.083 customer. Next, average waiting time in the queue, which is WQ, which is equal to LQ by lambda. Substituting the value of LQ and divided by lambda is 10 per hour. Simplifying, you will get 0.0083 hours. Next, problem 2. A telephone exchange has 2 long distance operators. So here also channel is equal to 2. The telephone company finds that during the peak period, long distance calls arrives in a Poisson fashion at an average rate of 15 per hour. The service time is exponential with a mean of 5 minutes per call. So it means you have to take mu equal to 1 by 5 per minute. Find the probability that a customer has to wait for his long distance calls during the peak period. That is first subdivision. Second subdivision, what is the expected waiting time including his service. Okay, solution. This is of model 3. Number of channels are 2, lambda 15 per hour, mu equal to 1 by what? 1 by 5 per minute. So okay, 1 by 5 into 60 is 12 per hour. Same formula P naught, already we have seen this formula. Summation n equal to 0 to c minus 1 lambda by mu whole power n by n factorial plus lambda by mu whole power c by c factorial into c mu by c mu minus lambda to the whole inverse. Substituting c equal to you see the first term, summation n equal to 0 to 2 minus 1, 15 by 12 whole power n by n factorial plus 15 by 12 whole squared by 2 factorial into 2 into 12 by 2 into 12 minus 10 to the whole inverse, and n equal to 0 to 2 minus 1 is nothing but n equal to 0 to 1. So you have to substitute n equal to 0. For first term you have to substitute n equal to 0 and n equal to 1. You will get totally 2 terms. Simplifying first term you will get 2 terms. So third and fourth terms are simplification only. For third term you see lambda by mu means 5 by 4 whole square by 2 factorial into 24 by 14. Simplifying will get P naught equal to 0.2308. And first subdivision, the probability that a customer has to wait for service. It means probability of WS greater than 0. This formula you have to use lambda by mu whole power c by c factorial into 1 minus lambda by c mu into P naught. So 15 by 12 whole square by 2 factorial into 1 minus 15 by 24 into 3 by 13. Simplifying you will get 0.4808 hours. Next subdivision, expected waiting time in this system, which is WS. So this formula we can use LS by lambda, or this formula also we can use lambda by mu whole power c plus 1 by c factorial into lambda c into 1 minus lambda by c mu whole square into P naught plus 1 by mu. So here lambda is 15. 15 by 12 whole power 2 plus 1 divided by 2 factorial into 15 into 2 into 1 minus 15 by 24 whole square into 3 by 13 plus 1 by 12. Simplifying you will get 1 by 2 into 1 by 30 into 125 by 64 into 64 by 9 into 3 by 13 plus 1 by 12. Use calculator and simplify, you will get 0.1368 hour. So 1 hour equal to 60 minutes. You have to multiply this with into 60. So that 0.1368 into 60 you will get 8.208 minutes. Okay, so you can mention 0.1368 hours meaningless, no? So you have to convert into minutes. So finally WS equal to 8.208 minutes. So now we have seen 3 models, model 1, 2 and 3. In the next lecture, video lecture series, we'll see model 4, that is MMC NFCFS, that is the last model. So remaining we have one video lecture is there. So in this lecture we are going to discuss about model 4, that is MMC NFCFS model, and PK formula, Pollaczek-Kinchain formula, that one is non-Markovian queuing models. We will see 2 more problems in PK formula and 2 problems in MMC NFCFS model. We will see totally 4 problems we are going to see in the next video lecture series. Okay, so I hope all you understand well. So work out more problems. Okay, refer your book for more problems. Okay, completely you have to work out all the problems. Okay, thank you for watching. Thank you students. Have a good day.